Alright, so the final thing I wanted to mention for this module uh, has to do with example 1.3.6 from the book. And it's given there is we are asked to take a look again at the set S of rational numbers set S of rational numbers such that r squared is less than 2. Sorry about that. So, as mentioned in the previous video, we turn actually this set here into a cut by adding all the negative numbers. But this is just for matters of constructing and discussing the riches of dealing with cuts and how to embed them into this new system of real numbers. But for the sake of just obtaining the square root of 2, this portion of that set, of that cut, is enough. So what we want to say is the set is going to be bounded. So that's the first observation. So this is a set of rational numbers, right? So this set is going to be bounded in Q and is therefore going to be bounded in R. If you have a bound in Q, then that bound lives also in R, and therefore a number set that is bounded in Q will definitely be bounded in R as well. You don't lose the property of being bounded by adding more numbers in your system. Because in addition you have the property that R is an ordered field. So whatever, this particular set defined in this way consists of the rational number set to R squared is less than 2. So all the numbers all the numbers such that the squares are less than 2 can be ordered within the real numbers. So again, that's why you can combine this with my previous observation about the fact that you don't lose anything by adding new numbers, which is what we've done. The set S is bounded in Q. So we'll receive for the moment the discussion here to Q. So the set S is bounded in Q, and to see this it suffices to recall that if R squared is less than 2, then R is less than 2 itself. And why is that? Because if R were greater than or equal to 2, that would imply that R squared would be greater than or equal to 4, which is strictly greater than 2. So that means that R has to be less than 2. right? So R is, so that means that 2 is a bound, an upper bound. So so in the same way, we can show that -2 is a lower bound. And then notice also that, well, of course, I mean, we claimed that the set S was bounded in Q, and is, so the bounds have to be in Q, but -2 and 2, they are both integers, and in particular rational numbers. Okay, so that's how we conclude that S is bounded in Q. This is a key point here, in Q. It will also be bounded in R. Okay, so now, so if we were in R, we were working inside the real number. To say that the set would have a supremum. Right, so if instead of defining S as a set of rational numbers such that R squared is less than or equal to, no, less than 2, we had used the R's in R such that R squared is less than 2, then the set would be bounded again by 2 and between -2 and 2. And so we would have that by virtue of the least upper bound property, the set S would have a least upper bound, namely a supremum. But since we're working in Q, that is actually not the case. And in fact, this is not the case for S. Which is defined in Q. If S had a S had a supremum, this number necessarily have to satisfy supremum of S squared would have to be equal to 2. But such a number cannot be a rational number. right? There's no rational number such that its square is equal to 2. And so what we conclude here is that the supremum property, so the least upper bound property, cannot hold within Q, and that's why this is a very valuable thing to have, what we've accomplished here. So, and to see, I mean, we will see actually that the supremum of the course, the a modification of S, where you include real numbers, is actually a a, the square root of 2. I mean, a valid way of defining root of 2. In fact, let me correct something I said. I mean, you can do that. I mean, you can certainly correct this by adding real numbers such that r squared is less than 2. But as it is, since there are numbers in Q, S is still a subset of the real numbers, and it's still bounded. Okay, so since we have the least upper bound property for R, we can see, however, that S as a subset of R now is bounded, and the supremum of S exists. Yeah, the supremum of S that we're referring up here is a supremum in Q. Right, this is a number of Q. We're trying to explore what would happen if there was a supremum in Q. That supremum cannot exist. A supremum in Q. The S doesn't have a supremum in Q, but it has a supremum in R, and this supremum is finally the number we've been after since the beginning of the semester. That is square root 2 is equal to the supremum of S. And the supremum in R, which exists in R. The supremum S it exists in R. So that's the first accomplishment we'll mention. And how do you prove? Okay, so now we already know that the supremum of this set S will exist in R. So how do we obtain that the supremum has to satisfy the supremum of S squared is equal to 2? Well, if you have an upper bound for this set, then R squared must be greater than or equal to 2. because of that remember the whole discussion, if we have a number such that the squared is squared is greater than 2, then that has to be, if in the number is positive, there has to be an upper bound for s. We discussed this last week or the week before that, and that's because the function r squared or x squared is increasing in the rational numbers or the real numbers. I mean, because the order is going to be preserved. Okay, so it's 1 to 1 and it's increasing. So you can also go back and forth and it's the same thing. So the function r squared keeps the ordering. If you look at the positive side of the rational numbers or real numbers, if r1 is less than r2, then r1 squared is less than r2 squared, and vice versa. So if r1 squared is less than r2 squared, then r2 is bigger than r1. r1 is less than r2. Okay, and so if you have a positive number that is an upper bound, then its squared must be greater than or equal to 2. Assuming that it's greater than 2, then the same kind of manipulations that we did before, if we subtract this really small number, its square would still be greater than 2. So it's still bound every number inside the set S. And so that would certainly not be the least upper bound. And so the only possible conclusion here is that then that supremum must be equal to a number r squared such that a number r such that r squared is equal to 2. So that follows the same kind of ideas and that we've used in previous modules. And so that number that satisfies a very good property that its squared is equal to 2 exists, and that it extends for all positive numbers, not only positive rational numbers, but our definition of R. So the construction of R allows us to define to say that the square root exists for any positive real number. Simply by replacing here 2 by the real number that you want to compute the square root of. So if you put any number alpha instead of 2 in here, so if you were to put a number alpha in here, again, because of that increasing property of the function x squared, even within the real numbers, you see that this and on the order field properties, you see that this set here will be bounded for the set defined with alpha instead of 2, and therefore we'll have a supremum, and that supremum will have to be the square root of alpha. Okay, so that's one first accomplishment when we deal with now with the real numbers instead of the rational numbers. Okay, so one next thing that we want to say now, so the next thing, the next step now is to so now in the next module, what we'll be doing is we'll obtain useful characterization of the supremum, and some properties. Of the supremum related to some transformation of subsets of the real numbers. So what do we mean by this? So useful characterizations are sometimes, or of course we already have a definition of the supremum, that's at least upper bound. But in practice, when we want to show that something is supremum, it may be more convenient to consider something that actually implies that, based on if and only if. So this is a very useful property that tells you that you have to, whenever you subtract something from the supremum, I mean if the supremum is finite, subtract something from the supremum, however small it is, you must be able to find an element in the set that is slightly bigger than that. And that's a very useful characterization. It allows you to prove things. I mean, how do we, well, what allows us to say that it's a useful characterization? Is because it allows us to prove theorems and lemmas and stuff like that. And so we'll be applying this new characterization of the supremum and infimum to some problems. And at the same time, we will show we use them in to show some more fundamental properties of these supremums and infimums, supremum and infimum notions related to some transformations of sets of R. So what do I mean by that? If you translate a set, so you move it to the right or to the left, what happens to the supremum? The supremum will be translated by the same amount. If you dilate a set, then the supremum will be dilated by the same amount. This sounds very intuitive and very easy to prove, but you'll be surprised at how many students struggle with actually showing this. So we'll be going over these properties then next time, and now that we started doing analysis, things are going to start becoming a little bit more computational and more hands-on. But I hope that the foundation that we've built is strong enough now. Okay, so see you next time.